In the last video, we got to the point where we made this graph of stress versus strain for our aluminum sample, which was pulled apart. It was right here. And we talked about how this graph can be made, and where we're initially in the elastic region, we start to stretch it, and if we let go, it'll go back to its original shape. But at some point, with enough stress or applied force per unit area, we start to distort the material. We get into the pink regime here, which is the plastic deformation. As you can see here, yeah. So it's elastic in the blue, plastic in the pink, and then we have this all sorts of structure here. So we're going to use our data to find things like the slope right here, and ultimate tensile strength, and then maybe the failure strain. In other words, what's the percent that it actually stretches before it fails? So let's take a look at that. So the first thing we can do, for any graph, you really should have nice big labels. So I'm going to double click over here, and I'll be honest with you, I just kind of play around with this because I don't know where everything is located. I just kind of look over to the right, and the user interface people at Google have gotten a few things right. I can generally find things. So let me make these nice and big. The numbers, I guess you can't go too far on this. Let's see, I want these numbers, the font size, let's call that 24. Okay, so we can kind of see what's going on here. Also, typically these are not shown as data points. We're going to leave them as data points, but I think it'd be nice to put in a line. Would you agree? Let's see. Trend line? No, not trend line. We'll use that later. I know there's a way to do it here. Let's see. Fill color, point shape, point size. I think I need to change maybe the entire, change it from a scatter to like this one here. What if I click there? No, that was what I had here. Okay, let's use this one. So a line chart. So we still have the data points here, and I'm going to accentuate those maybe a little. Let's see, fill color, let's make that red. Will that do it? No, that didn't do it. Okay, well, I do want to see the points. Let's see, point size, let's make it 10. There we go. And now I wish that other one wasn't red. Let's take this guy and not make him red. Sorry about this. I'm just kind of, as I said, I just kind of play around here until I get it to look right. Okay, we're going to leave it like that. And so what happened to the size of our labels? Again, labels very important. I have no idea why that happened. Let's also put up here, this is aluminum. And I think that should be bigger at 30 or so. Okay, here we go. All right. So this is our graph, and we're going to eventually capture this and put it into a presentation, and we're going to be able to label it. So let's go ahead and do that now. So I'm going to take that off, and I'm going to use my snipping tool, and I'm going to grab the whole thing right here, and I'm going to put it into my, why is that not working? That's very interesting. Huh. New slide. Control M didn't work. Okay, there's our graph. Let's first find the ultimate tensile strength. So that's going to be the maximum stress. And there's an easy way to do that. Let's go back to our data here. So here's our data. What I'm going to do is I'm going to come to the very bottom, and I'm going to say equals maximum, left parentheses, and then I'm just going to go ahead and grab everything here, enter. So this is going to be the maximum value of the strain. So it's about 17.5%. And now I'm going to Control C, Control V, and so that's going to be the maximum stress. And this is going to be the maximum strain. Like so. And to get that one to fit, I think I got to do that. Okay. So these values, maybe we'll give them the color like yellow. The maximum stress, remember stress is on the y-axis, is 63,180 psi. 63,180. So that is the maximum value here. So that's somewhere over here. Okay, let's see if we can find it. 63,180. Yeah, I think that's it. 63,180. That's right. So it's right there. So we're going to come over here to and we're going to place an arrow and say, you can hold down the shift key to make sure it's vertical. We're going to put an arrow on both sides, and then we're going to put a max tensile strength is 68, what was it? 68,180 psi. I got to check that. let's give that a background that kind of stands out a little bit, yellow, and a border. Okay, so that's that one. I think I got to check that number. I think I may have gotten that wrong. So let's go back to our data file, 63,180. Let's just leave it at that. So if I come back here, 63,180, not 68. 63,180. Okay, so that's the maximum tensile stress, tensile strength, ultimate tensile strength. Let's change that to ultimate. Ultimate tensile strength. Let's see, what is that? Let's do the maximum strain. So the maximum strain, we can take this double arrow, copy paste, Control C, Control V, and we can come along here and pull it over here and hold on the shift sign so it's parallel or horizontal. And again, I can copy Control C, Control V, and I can write here. So maximum strain is, what is that value? Come over here, 17.5%. So 0.175. 0.175, it's unitless. So it stretches by almost 17.5%. So let's write that. Stretches 17.5%. Remember, that 0.175 is the normalized to the original length before breaking. It's pretty amazing. I think steel is like 25%. So we'll have to compare our results to results obtained from professional, folks. I think this will be okay. Let's make these a little bigger. All right, it's getting a little messy there. That's okay. All right, so what is our, let's come over here. And I'm going to say about right there is the, what is the term we want to use? It's the proportional limit. Looks to be, I'm going to say right there. Proportional limit is at 48,288. Proportional limit, 48,288. So I can come back here to here, and let's again take our Control C, Control V. We can just copy that. So proportional limit is right there, we'll say, and that is 48,288 psi. Is 48,288 psi. So past that point, it starts to act like taffy. Okay? And so the yield point, I think, is just a little bit past that, and we can call that one, well, this is kind of just not all that precise, but the yield point, 50,243. Let's go ahead and put yield point, what was that, 50,000, I know this is wrong, 233, I'm pretty sure that's wrong. Let's go back and check it. 50,243. 50,243 psi. Okay, so how do we make that look the best as we can? Let's just go ahead and take one of these, and we'll say it's right there, like so. One of those arrows. We'll come over here, and another arrow, say right there. Yield point, proportional limit. Oh, we need the last one, the slope of this line. So that's going to be a tough one. So I'm gonna go from 0 all the way to the 48,288. And to do that, what I'm going to have to do is come up here, and I'm going to grab the data and go up to 48. So just that data is the linear part. So I'm going to right-click, copy, and I guess I'm going to place it over here. Control, I think I need to do one of these just to make sure my formulas turn out right. I'm going to do an edit, paste special, and just paste the values. So it's going to paste the values only, not the formula. So actually, I think that would have corrupted the those numbers. But again, all I'm doing is copying that linear part. So now I'm going to grab it, and I'm going to make my own insert chart. See, it's pretty linear. And I'm going to come over here. I'm going to give it its own sheet. And I do want to have the points so I can see them. Okay, fair enough. Okay, so this is going to be stress versus strain. I'm going to double click here in the linear elastic region. So, and again, I'm not going to do it in this video, but you really should make these bigger so you can see them like so. No one wants to strain to see what the axes are. So maybe I will just quickly try to do this. Okay. And then here, well, okay, we'll do that later. So here's the main point. We want to find the slope of this, so I'm going to, there it is. So we can come down here, and Google knows that we probably want to do something like that. So I'm going to go to the series. So among all the choices here, chart style, chart, and axis titles, go to series. That's basically the data. And you can put in a trend line, like so. And we're going to choose linear, which is a default. I'm going to make the line color red to distinguish it. And there it is. So I'm going to show r squared. That's a measure of the fitting of that line. But I also want to find the slope. So where is the slope? Label. Use equation. Okay, there it is. So right here we've got the slope of the line, 2.56 times 10 to the 6, x plus 3498, with an r squared of 0.98, which is quite good. So let's make this bigger. Why are we straining to see that? That's like the whole point of the graph. Can we get any bigger? I guess we can manually do it. Let's make it even bigger. There we go. So 2.56 times 10 to the 6 is the slope of that line. And it is, there it is. And it is the modulus of elasticity. So let's do that. 2.56 times 10 to the 6th. What is that? That's 2.56 million, right? So let's go over here. And we'll come over here. So let's grab another box. Control C, Control V. We'll come over here. So slope of linear elastic region is the modulus of elasticity. So E, we'll call it equals 2.56 times 10 to the 6th. And what are the units of that? Well, rise over run. The rise is PSI, and the run is dimensionless, so that's going to be in PSI. So we'll have to compare that to what the textbooks say about the modulus of elasticity of aluminum. But I think we have most of the important stuff there. We've used the graph to display it. We've used the spreadsheet. It's served us very well to find everything we need. And yeah, that is how to interpret a stress strain curve for all this important information about various materials. Thanks for watching.